Hey, what's up, guys? Chung here. So today, let's take a look at this hard LeetCode problem, number 1203. Sort items by groups respecting dependencies. Okay, I think the name of the problem is a little bit confusing, right? So let's take a look what's this problem it's about. So there are like n items, and each items belonging to m groups, zero-base m groups. uh, where group I is the group that I's item belongs to. Okay, and if this item doesn't belong to any group, the value in the group array will be -1. Okay, and okay, so both the items and the groups they're both zero index. They're all zero based, and the group can have no item belonging to it. So, and it asks you to return a sorted list of the items such that the items that belong to the same group are next to each other in the sorted list. Okay, it means that if there's there are like four items in the group one, so all those four items uh, should be together. And not just that, we also have like a before items list. It defines some relationships between those items. Basically, the before item is a list containing all the items that should come before the ith item in the sorted array. And yeah, and return any solution if there's more than one solution, and return an empty list if there's no solution. Okay, I guess this problem is already kind of confusing, right? Because there are many, basically there are like four inputs, 1, 2, 3, and 4. And then in the end, it asks us to return a single list here. Uh, so first, right? So first one is this group here. Let's say, for example, we have a group here. So the index means the group index. Okay, it means that the first node does not belong to any group. The second node, same thing, and the third item belongs to group one, and the fourth one belongs to group 0, and 0, 1, 0, and -1. Okay, so that's for the group. That's for the group one, and this one before items, basically the first one. So item 0 doesn't have any I mean dependencies, basically, right? So if we draw like a graph here, okay, uh, so at index 1 here, so 6 has to be before the index 1. 6 needs to be appear before 1. So it means that there's like a edge from 6 to 1. Okay, how about this one? 5 needs to come 5 needs to needs to appear before 2. So we have a 2 to 5. Sorry, 5 to 2. And same thing, 6 needs to appear before 3. So we have a 3 here. Okay. Now 4, 3, both 3 and 6 needs to uh, appear before 4. So we have a 4 here, and then we have a 4 and 4. Okay. As you guys can see here, so now we have a directed graph, or you can call it a DAG, directed acyclic graph. Okay. I mean, if it only asks you to find just to output the nodes based on the sequence of the directed based on the DAG here, it will be a medium problem. But what makes this one a hard problem is that on top of this layer here, right, we have another layer of the graph. which is the group. And what does it mean is we cannot simply just do a topological sorting based on the graph here. Okay, you know, so currently we have a group here, right? So the group is like so for in this example, right, the group 6 is belongs to group uh 0. So 6 belongs to group 0, and 3 is also 0. 4 is also 0. 1 belongs to group basically belongs to its own group. Okay, and then 5 belongs to 1, to group 1, and 2 also belongs to group 1. Okay, so that's why I mean the basically one of the example will be for from 6, 3, 4, since all three belong to the same group. That's why we have to output them all together. Okay, and it means that we have to do the topological sorting group by group. Okay, and so in order to do that, we have to create a hash table to store all the nodes for each group. And within each group, we'll create like a helper function to do a topological sorting within that group. And that's within the group, right? So, but how about then we also need to sort uh, among the groups. Why is that? Because uh, let's say we have group. So now we have a group 1. So this one here, right? For example, here the one here, this one has a like, let's say it has a group uh, 8. Okay, and in order to get 1, basically we have to process group 0 first. So no matter what, the group 0 has to be processed before group 1, before group 8. Okay, and within the group 0 itself, the order has to be 6, 3, and 4. Okay, so that's the sorted order in for group 0. That's for group 0. And for group 1, it has to be 2 and 5. Okay, that's for the group 1. And so here there's like a group, for example, let's say there's a group 8 here, right? The group 8 is 1, and the group 0 has to be sorted before 1. But for the group 1, sorry, the group 0 has to be processed before group 8. But for group 1 here, it doesn't really matter. It could be either at the beginning or at the end, because group 1 does not depend on any other groups. Okay. And every time when we do a topological sortings, right? Let's say when we sort uh, this group 0, it also give us like another example here. Let's say let's say for example, let's say the number 3 belongs to group, not belongs to group 0. Let's say the number 3 uh, belongs to group 1. Okay, then there will be like a cycle basically. Why is that? Now uh, now the group 1 is depending on group 0, but here see, but here the group 0 also depending on group 1. Basically we're having like a cycle uh, in terms of the group dependencies. In that case, we need to return the empty array. Okay. Yeah. Mm, cool. So let's try to code these things up here. Okay. Okay, and that's the first case scenario that will cause like a cycle, which is the a cycle among the groups. And the second one is within the group. Okay, so let's say, for example, we have a, I'm going to remove, oops, I'm going to remove these things here. Uh, 3, still 0. Another one is that if there's a if there's another edge from 4 to 6, okay, as you guys can see, now we have another cycle within the group 0, right? And this will also be a invalid group. So in this case, we'll also need to return an empty array. Okay. And how do we check the cycle? If the cycle exists in the graph, basically we just do a topological sorting, and in the end we check the length of our result. If the result is the same as the number of the nodes, if it is, then we know there's like if it's the same, then we know okay the valid there's no cycle. But if the answer if the returned list is smaller, it's shorter than the original list, and then we know we have a cycle. Okay, cool. So the coding, the amount of code will be a little bit more in this case, but just stay with me. Okay, so first, like I said, since we're going to do a topological sorting uh, for both the group itself and among the groups, and I'm gonna create like a utility method just to do a topological sort. And I'm going to pass 3 parameters. The first one is the nodes. Okay, it's the node we're trying to sort, do a topological sorting. And the second one is a graph. Okay, and the third one is a integrate. If you guys still don't know how to do a topological sorting, I suggest you to look at the wiki page. Basically, the way we're doing the topological sorting is we always starting from the zero integrate nodes, and every time when we have seen like zero integrate nodes, we'll be removing the edge from the graph, which means we'll be for the neighbor nodes we'll be decreasing the integrate for that target nodes by 1. And every time when we have a new zero integrate node, we add that to our queue. We just keep doing that until the queue is empty. Okay. So basically the queue will be the collections.dequeue. Uh, so first at the starting point, the anything that's not in the graph, that's any node that's not in the integrate will be the node that has the zero integrate. Okay, for node in nodes, if node not in integrate. Okay, so that's the first the starting point. And like I said, we're gonna have an answer great array here, and then we just do a while loop here. Okay, and current node equals to what? Equals to q dot pop left. Okay, and okay, every time when we pop a node, we append it to the answer. Okay, and then just do a neighbor like in the graph. Okay, current node, and then we just decrease the integrate. Okay, for this neighbors by 1. Okay, if the integrate if after decreasing by 1, if this thing is 0, then we just append these things, append the neighbor to the queue. Okay, in the end we simply return the answer. So that's the basically the topological sorting, the helper functions. Now uh, now let's do this. Let's try to create like a group items group items hash table so that we can group all the item for each group. Okay, so we're gonna have like group items, right? In gonna be a default dictionary, a list. Okay, for I in range n. Okay, and oh, one more thing. So as you guys can see, we might have some items that has its own group. It doesn't belong to any group, but to help us solve this problem, we're gonna give those items which has a group -1 its own group. So we can give it any number, right? Mm, but it cannot be the same. But it cannot be the same as the group from 0 to m. Okay, since we have 0 to m-1 groups. Okay, we can simply uh, uh, like the group ID. Okay, we can do group ID starting from M. That will be sure those -1s will have its own unique group ID. Basically, so if the group I, right, is equals to -1, then we know, okay, we need to create a new group for those. Group ID. mm, so the group I, okay, so the group I will be group ID. Basically, I mean, if we don't do this, right, all those items, they will be categorized with to the minus one group, which is wrong. That's why for each of them, for each of those separate item, we're assigning a new group ID to it, and then every time we just do a group ID plus one. Okay. Okay, and then after that, right? So the group IDs, the group items, and then the the value will be the group ID. Okay, and we do append I. Okay, so with this for loop here, so not only we are like assigning the item to its group, we also create a new group for those items that does not belong to any group. Okay. And cool, so that's that. And now the second one will be we'll be building the graph and integrate for the within each group. Okay. Uh, graph. Let's call it item graph. Okay. Default list, and then the item integrate default integer. Okay. For v and u list. Okay, u list enumerate before items. Okay, so since so the v is okay, so here it's like the edge is from u to v. Okay, u and v, right? So that's how we usually define like an edge. Basically, the index will be the v. Okay, and the value is the list of u, right? So that's why I mean for u in the u list. Okay, so now here, be careful here. So now we are only trying to build the graph, I mean, within the group. Okay, so which means, let's say if we have a 6, 3, and 4. Let's say this 6 and 4 belongs to group 0, and number 3 belongs to group 1. Then we don't want to like uh, build the graph for the across different groups. So basically, we're building the graph only for the same group. So that's why. So if the group U is equal to the group V, so if that's the case, we're gonna do a graph. Okay, U dot append V. Okay, so why is that? Because we only want to because later on when we process those nodes here, since since all the items within the same group has to be together, that's why we we will not include this one. Otherwise, it will give us like the wrong answer. Okay, and then the item, same thing. The item integrate of the V will be increased by 1. Okay, uh, cool. So now we can process each groups. Mm, yeah, we can do the topological sorting for each group. So let's see how we can do it. And mm, we have group items. Yeah, so basically the way we're doing it, we're gonna do mm, for each group. For each group ID, okay, for each group ID in the group items, right? Since we already built these group items, so we just need to get all the list and sorted. We're gonna create a sorted nodes, sorted items, okay, equals to the topological sorting. Sorting the nodes will be the group items with group ID, right? That's our that's the total nodes we need, okay? And then the graph is the item graph, and the integrate is also the item integrate, okay? So now we have sorted items here, okay? So now we can do a simple check here. Basically, if the length of the sorted items is not it does not equal to the length of the passed in nodes, okay, then we know there is a cycle, okay. We can simply return empty, okay. Otherwise, we just need to store those items. Okay, yeah. In order to store those items, let's create another hash table here. Sorted group items, okay. Because later on we'll be using this sorted group items to construct our final answer. So sorted group items, so the key will be the group ID. The value will be the sorted items. Okay. Basically, we're topo sort for within each group. Okay. So that's to sort the within each group. Now we need to sort the do the sorting among the groups. So to do that, we also need to build a graph. Okay, now we have a group graph. Same thing for default list, and then for the group integrate int. So how can we build the uh, the groups, right? So same thing here. We're gonna basically copy most of the things here. Basically, we're gonna also do a VU list enumerate before items. Okay, for U in U list. Okay, if the group U is not the same as a group V. Okay, basically, if the edge coming from two different groups, then we have a dependency, right, between the groups. What we have is we have the basically the group graph from group U, okay, to the group V, okay, and then we have a group integrate here of the group V, okay, plus one, okay. That's how we build the group graph and the group integrate here. And we just need to do a sorted group here. We need to do another topological sorting, right? By calling the topological sorting helper function here, okay? Topo sort. Now the we need all the groups, okay? The groups will be okay. Yeah, let's create the groups here. So the groups will be a what? Will be a set of the group okay? Because at this moment, right, since we have already assigned each of the group here, and basically we need the unique group ID here, right? That's why we do a set. We convert this group ID because as you guys can see, there are some like duplicated element in this group array here, and we once we convert to a set, now we have a unique groups here, and then we have a group graph, okay, and the group integrate, okay. So after calling this here, uh, among groups, we can do a simple check here, right? So same thing. If we can, we just need to check if there's a cycle between the groups. The length of groups is not equal to the length of the sorted groups, right? Then we also need to return like empty. So if all this check passed, now we know, okay, we can construct our final answer here. So the answer will be that, and I think we just need to loop through the groups, okay? For group ID in sorted groups, okay? Answer dot extend, right? We just need to extend that. We extend what? We have a sorted group items because within each group we have already stored the sorted result into this hash table. So we just need to get them out, right? Group ID. And then we append those lists to the final answer. And in the end, we simply return the answer here. Yeah. Uh, let's try to run it. Syntax error. Line 15. Oh, 0. Okay. Neighbor, okay. A typo here, neighbor. Run default. Line 51, okay. Yeah, I think because the code is kind of long, so I have many typos here. Unhashable type list. Line 70. sorted group. This is ID, right? Sorted group here. Unhashable. That's weird because this sorted group is the it's a list, right? And nodes. Okay, let's see. Uh, so let's see. Unhashable type list. So it means that we have a list in here. What are we returning here? Answer. Oh, here. So we should append the current node, not the answer. I think that's why it instead of a node itself, it's returning like a list because we are recursively like appending this answer. Okay. Let's try to run this. Okay. Uh, yeah. Submit. Cool. So it passed. All right. Um, yeah. So basically, this problem, just to recap real quick. So this problem is it's a hard problem, and it's basically it has two layer of like topological sortings. And so first we create like a helper functions to help us do the topological sortings for the given nodes, the given graph, and the given integrate. And it returns the sorting, the topological sorting for the given for those given three inputs. And then uh, and then the next one, basically we are uh, we group items. Okay, we group items into its own group so that we can use those the group items to do the topological sorting within the group. And while we're doing that, we're also like assigning those -1 group with its own group ID. Okay, so and then we're building like the graph for the for each group for for the same group. That's why we're doing this like the if check. Basically, uh we're only building an edge if the from and the to are within the same group. Okay. And then after that, we for each of the group items itself, we're doing like a topological sorting. And after that, we check if there's a cycle within each group. If no, we simply assign the result into this hash table so that later on we can use this one to build our final answer. So that's to sort each within each group. Now the second one is we have to also sort uh, among the groups. That's why we're building like another set of the graph and integrate uh, hash table, hash table, and we're doing this. We're looping through the related dependencies, and now this time instead of checking if the group are the same, we're checking if the group are different. Because if the group are different, then we have a dependency among the groups. That's why we are adding the groups dependencies into the group graph, also into the group integrate hash table. And then now we just need to do a topological sorting, right, for all the groups. If and then we just check if there's a cycle among the groups. If everything works fine, then we can simply construct our final answer based on the sorted groups. And then for each of the group ID, we get the sorted result for this group. and then in the end, we simply return the answer. Cool. I think that's pretty much it is I want to talk about for this problem. Yeah, it's a good problem. It's a good practice, especially for the graph, for building the graph and for like using the topological sortings. Yeah, I hope you guys like the videos, and thank you so much. And I'll be seeing you guys soon. Yeah, bye bye.